Oh, hey, how you doing? Just up on this ladder doing some home repairs. I hope you find this lesson illuminating and that it brightens your day. Hello there and welcome. We're now in Unit 2, the relational model. Let's get started. So here's what's on the agenda. What is a relational model and why is it so popular? What are the elements of the relational model? Let's take a look at how the DBMS implements the relational model. So there's a slight difference between the theoretical aspect of the relational model and how it actually gets put to use in a database management system. We'll also take a look at tables and relations in detail. We'll take a look at the concept of keys. We'll talk about more keys than you probably want to know about. We'll look at data domains, null and flags, and we'll finish with referential integrity. That's what connects the tables together. So before we do that, let's just take a moment and go back and recall the different implementation models that are out there. So we had the relational model that we're talking about this week, and then we also had these ones down here, which were part of the NoSQL movement. These other models are more specific to a certain need, whereas the relational model tends to be a great general purpose data model. That's why a relational has sort of survived for as long as it has, is that it's just general purpose and meets a wide variety of business needs. I wouldn't say that it's really good at any one thing at scale, but it's by far the best known and the easiest to get started with, and also without a doubt the model that you can really sort of use to kick off your database understanding, so that when you look at these other models, they'll make more sense to you. So it's a great model to start with to learn. So why is relational so popular? In practice, the relational model has been around for 30 plus years. It was conceived almost 50 years ago. So what makes it so popular? Well, one is data independence. How the data gets stored in the database as files is independent from how it is accessed. You do not need to know anything about the physical storage mechanisms in order to retrieve or write data to a relational database. It uses SQL, which is an easy to learn query language. It's what's called a domain specific language. You can't write a complete application in SQL, but you can write data logic, which allows you to query data and then mainly do the data management operations, create, read, update, and delete. And there's also some other types of logic you can combine together in there. Again, it's been around for a long time. 50 years of existence means that there are a lot of implementations. It's well known. It's mature. There's many places that you can find it, out there in the wild being used. So let's talk about the components of the relational model. So one of the primary components of the relational model are tables. And tables are two-dimensional structures of persistent data. So persistent meaning, you shut off the DBMS, you turn it back on again, the data's still there, right? It survives power outages and power cycles, right? It's there permanently, unlike the data in RAM, which in random access memory, when the computer gets shut off, the data's lost. So the table is a collection of items to be stored, and in the rows, we have distinct items, and these are known in the relational model as a tuple. So this Chevy Bolt here is one tuple, and then this Hyundai Ioniq at the bottom is another tuple. So think of the rows as discrete values So if you're thinking about what we talked about last week, they would be considered objects. So, this is a data as object, and then this is one piece of atomic data, right? So leaf represents this tuple's model. So that ends up being one atomic piece of data, whereas Nissan Leaf, $34,190, 149 miles in its range, that ends up being the tuple. Okay. So each column is a set of acceptable values, and this is called a data domain. So, for instance, this range in miles, I wouldn't expect to see the word bolt in here, because that's not the purpose of this column. Now, there's bolt over here, so one of the things about writing a tuple is that you need to make sure you put the right atomic values in the right column. Right? The column ordering physically does not matter. This is another nice thing about the relational model is the row dependence and the column dependence. There is none. It doesn't exist. So what does matter is when you find this column, you adhere to its data domain. So here's another example. This is a data domain for retail price. I would expect to just see, the cost of each of these electric cars. Okay. So again, you have your tuple in your row and your data domain in the columns of the table. And the tables are persistent. Let's talk about relations. So a relation is a very special kind of table where every single tuple can be uniquely identified. That is, there are no identical tuples in the table. So for instance, this table on the left is a relation, but this table on the right is not a relation, mainly thanks to the Nissan Leaf, which appears twice. This is acceptable in practice. You can have 2 or 3 or 4 or 5 of the same tuples in a table. However, if you have that situation, then that table is not a relation. A relation is a concept. There is nothing in practice in the database management system that allows you to say, let's create a relation. You're creating tables, but you do use constraints, data integrity constraints, to enforce relations over tables, as we will see. Let's take a minute and talk about how you turn a table into a relation. That is done through a primary key constraint, which establishes something called entity integrity. And entity integrity is a characteristic of a table which ensures that that table will be a relation. Meaning, we achieve entity integrity through using a primary key constraint. The primary key constraint is the implementation mechanism by which the table becomes the relation. A column or set of columns for which we tell the DBMS these values must be unique and present. That is, not null. Null meaning no value, okay, or an empty value. So, in other words, when we make our table and then we set a primary key constraint over one or more columns, what we're telling the DBMS is that there is no way possible for someone to add or update data so that the values in that column repeat. And therefore, that makes the table a relation. There can only be one primary key constraint per table in the DBMS implementation. So every table may or may not have a primary key constraint, but if your table has a primary key constraint, it can only have one. All right, so now it's time to do a demo. And in this demo, we will use the admin web application because we don't know any SQL yet. So I want to introduce these concepts to you, these relational concepts, without muddying up the waters by showing you SQL. And what we'll do is we'll make a courses table in the TinyU database, and then we'll make a column called course code, and we'll add some courses and then edit a course just to show you how add minor works. And then we'll demonstrate how the table is in a relation, and then we'll try to enforce a primary key constraint on it and show you that what happens when it is a relation. So this will really help sort of solidify and practice table versus relation. All right, so here I am in the add minor application, and I'm getting ready to log in to the TinyU database here. Okay, and I have. And so add minor is a really nice, convenient tool, but it can be a little overwhelming. So basically what you're looking over here is this is the database, and then the schema for now, we're just going to leave it as the default schema. A schema is a way to subdivide the objects that are in the database. Okay, it's like a logical grouping of objects. And over here you see the tables that are in the database. And what we're going to do right now is we're going to make a new table. So we're going to hit Create Table. And we're going to call this table Courses. Again, I can do this in the SQL language. We just don't want to muddy things up with the SQL language. We just want to focus on tables and relations and understanding the concepts. And then in here, let's add a single column name called course code. And that course code is going to not be an integer. It's going to be some type of character field. Let's make it a varchar, let's say 8. Collation, by the way, lets you define the default code page for the characters that get put in there, right? So, we want to stick to the default, so I'm going to leave it blank, which is UTF-8 with a Latin character set. And that's good enough for now, and I'm just going to save this table. And now I've got this table here, and I can hit New Item, and I can add some courses. So IST, 101, and then let's add, Accounting 120, and then let's add History 202, and then let's add IST 101 again. And so when I look at my table, you'll see that I only have one data domain in this table, and I have 4 tuples, and this tuple are the same values, and the table doesn't complain about that at all. It has no qualms about that. And that's because we have not set a primary key constraint on this table. And because we have not set the primary key constraint on the table, it does not have entity integrity. So let's try to set a primary key constraint over course code. This makes sense because for every single course in a course table, there should be a unique course code. You shouldn't have the same course in there twice. So let's see what happens when we try to modify this table. So to add the primary key, we need to click on this Alter Indexes. Now, it might be confusing to you as to why that is, but remember, a primary key is technically a constraint over the table. And what we're going to do is for the index type, we're going to choose primary. And what this is going to do is this is going to force the physical ordering of the data in the table to follow whatever columns we choose. So I'm going to choose course code. And this is the first one, and you can choose ascending or descending order. And then over here is what we're going to call this. So I'm going to call this PK, courses course code, and we'll save that. And when we do, we're going to get an error. Okay, and the reason we get this error is because we cannot add a primary key to this column because this column does not exhibit entity integrity. Now, the error doesn't really give you any indication of that. And this is one of the challenges with relational database implementations, is sometimes the errors are not super friendly. So let's go back to the actual data itself, and let's delete this row here. Okay, so now I only have 3 rows, and each row is unique. So now let's try to add that primary key constraint again. There we go. And now it saves. Okay, so we have a primary key over the column course code. There's only one column in the database. I guess at this point maybe I can add another column. Let's add course title, and let's make that varchar, and we'll just say maybe 50. Oh, and I got to allow null because I can't add a column that doesn't already have, if it doesn't already have data in it. So I got to at least allow nulls in there. And then now I can just look at the data here. And I can edit this one, and we can call this accounting 1. And then maybe we can make this one US history. And then we can make this one information in society. Good. Now let's add another row here. Let's add another row. And let's call this, IST 101, and then information in the world. And you'll see when I try to insert that, I violate a primary key constraint. It says I cannot insert duplicate key into the table courses. And the reason for that, again, is because this value already exists. So I need to give it a different course code to guarantee entity integrity. So basically, that's the difference between a table and a relation. The relation exhibits entity integrity. Entity integrity means that your table is a relation and that no two rows will be identical. That is, no two tuples will be the same. So there's a lot of papers that have been written and blogs, posts, and textbooks on how to build a good relational table. I'm going to distill this into the simplest form possible using what I like to call the don't repeat yourself rule of table design. That is the dry rule of table design. So when you're thinking about what goes into a table and what doesn't go into a table, remember to keep it dry. Each row represents a singular, distinct entity. So, for example, if you want to store information about students, at the intersection of the tuple student and the data domain in each column, there should be a single atomic value. So, a student can have two majors, right? So you shouldn't have a column called majors in the student table. That's not the right way to do it. You really need to think about majors going in a different table. And I know this is a lot to chew on right now, but the way to think about it is if you cannot put an atomic value at the intersection of tuple and data domain, if you cannot do that, then you need to consider using another table. And then using a foreign key, but we'll learn about foreign keys in a bit. So no single entity should span more than one row. So what it means to be a student should not be in 3 rows. Just like what it means to be to have 2 majors should not be in 1 column. And most importantly, if you follow these rules, you won't end up repeating yourself. Okay. So let's talk about keys now. So we learned about one key already, the primary key, and the primary key is a constraint on the table that guarantees that the values will be unique for the columns you selected. It's a way to enforce entity integrity. So a key in any table, a key is any table, a key is any value in a table which can be used to look up another set of values in that table or in another table. any value can act as a key. Some keys are unique. Those can be used for entity integrity. Some keys are not unique. Okay? Some keys are just conceptual. They're just ideas, whereas other keys actually get implemented somehow in the relational database management system. So let's throw a pun out here and talk about some key concepts. So one concept is the candidate key. A candidate key is any column which you could use to make the table a relation. So the worst candidate key is the super key. That is, you use the whole damn tuple as your candidate key, right? You want to avoid super keys as candidate keys. You generally want your candidate keys to be as small as possible, right? Because you don't want to introduce all these columns into the constraint. The more complex your constraint is, the more processing the database management system needs to do to accomplish its task. So the next idea is a natural key, and a natural key is, just as it implies, it is a unique value found in nature, right? Or sometimes it's found in business. So, a great idea, a common example of a natural key is someone's email, right? My email address, my Gmail address uniquely identifies me. You can't use that one, you shouldn't be able to use that one Gmail address to identify me and then 3 other people. Okay, so you can use that email address as a natural key. Other types of natural keys exist in the wild, like vehicle identification numbers, social security numbers, employee ID numbers, right? So these are known as unique throughout the business or the organization, or just because of the way the world works. That's what makes it a natural key. Natural keys make good primary keys, but there are some times when you don't want to use a natural key as a primary key, and we'll talk about that. So that brings us to a surrogate key. A surrogate key is a way of saying, I don't like my candidate keys, I don't want to use my natural keys, but I need a primary key. So what I'm going to do is I'm going to let the DBMS generate a unique value for me. So you'll always guarantee that the row is unique, because the surrogate key will generate the unique value for each row. The advantage of this is you don't have to think about it. The disadvantage of this is, do you really have entity integrity? Because they're made up numbers, right? I can insert myself in there twice as a student because I'm guaranteed to have entity integrity, because the surrogate key ends up being the primary key. So, there's ways around that as we'll see as we get further into learning about the relational model. But at this point, I just want you to understand these concepts. There's also the idea of a secondary key, and a secondary key is a concept. Okay, there's no way to create a secondary key in a DBMS. A secondary key is used to retrieve data from a table, and it need not be unique. So secondary keys are ways that you look stuff up. Like, for example, you might have a table of students, and then you might try to find a student by their last name. So in that case, you're using last name as the column, the data domain of secondary key. Last name is being used as a secondary key to find the student, maybe find their GPA or their home address or whatever. So sometimes what we'll do with secondary keys is we will put indexes on them in order to speed up the search process. So if you have 1 million students, and rather than search through them linearly, you can build an index which reorganizes the data based on the secondary key, so we can find the data more quickly. And then there's another concept known as the composite key, and a composite key is just any one of these keys: a secondary key, a surrogate key, a natural key, or a candidate key, which consists of more than one values. So you might have a composite primary key, you might have a composite natural key, you might have a composite candidate key, etc. So let's do an example. Let's look at this table of students. You'll see I have various columns here. I have student ID, I have student first name, last name, GPA, and year. So this column over here, these numbers are automatically generated. If I add myself to this table, I will appear under student ID 8. So that is an example of a surrogate key. Maybe I want to use first name and last name to uniquely identify every student. Like, there is a tuck and roll in here, and there is a you're a quittin', but in my university, I don't have people with the same name. It's not very realistic, but it could happen, right? So in that regard, this would be a composite candidate key. Okay, now in real life, this is probably not a candidate key, but again, we're just playing with this toy example. Now let's suppose I wanted to search for all the seniors so that I can send them a congratulation notice, right? I would be using this column over here as a secondary key so that I can find those seniors. Now I don't have it in here, but if I had like the student email address, that would be unique for every student, and we would always know, without the use of a database management system, that that value was unique. And in that regard, that would serve as a natural key. Now, what you don't know is which one of these is primary key. That is, set as the constraint. Generally, the rule of thumb is that the value that's underlined when you present a table is the chosen primary key. So, like if you're taking a test and you see a table and this is underlined, then that means that was set as the primary key constraint. That's just generally the rule of thumb in practice. Ideally, what makes the primary key is that it's set as the constraint, right? All right, so now you're probably thinking, well, which one of these keys, my natural key, my candidate key, a surrogate key, what should I use as my primary key? So here's the rule of thumb. Natural keys are great choices. Surrogate keys are better because of how the DBMS physically stores the data by primary key. So let me demonstrate the issue at hand. If you set user email as the primary key constraint, you must specify the order in which the constraint is physically stored, ascending or descending. So I'm going to default this to ascending. So what happens is I write this person to the table, marry me off. I write this person, and then the next person comes along that I need to write. And unfortunately, that person alphabetically comes before Mary. So I actually have to do 2 writes now. Well, not 4, 2 writes, because I have to write I have to write Abby Cuss, and then I have to move marry me off down. And likewise, let's insert bet a lot, and bet goes between Mary and Abby. So again, I have to do 2 sets of writes. Now let's contrast this with using a surrogate key. Because the surrogate key is automatically incrementing every time, I only write once, and I write to the end of the table every time. So this is why you want to use a surrogate key to establish. Would be one reason why you would want to use a surrogate key as your primary key. Now you might say, well, Mike, how do I enforce unique values in the email column so that I don't violate the conceptual idea of entity integrity? And you're going to see that there are other constraints you can use to do that. So you're just going to have to trust me right now that using a surrogate key is a good thing. All right, so let's move on to another demo. Let's talk about the admin replication again. We'll alter that course table again. We'll add a surrogate key column, and we'll see what happens. And then what we'll do is we'll switch the primary key to the surrogate key. And then I'll then show you that now we can violate what was conceptually what we wanted, which is the entity integrity, but then we'll fix that later on with another demo. All right, here I am back in the add minor application, and I need to go back to my tables again, and let's go to the courses table, and let's take a look at that index. Okay, that index is still there, right? Now let's alter that table, and let's add another column, and let's call it course ID. And it's going to be an integer, and let's auto increment it. Oh, and I gotta do that. All right. So let's take a look at the table. Oh, it didn't do that for some reason. How interesting. Let's go back and see if we can fix that. It would help to click the auto increment button. So yeah, I got to click this little button over here and auto increment 1, save. All right, now let's go take a look at the table. Now there's still no data in there. Let's add a row. Let's edit a row. All right, interesting. Hold on a sec. Let me figure this out. Okay, I figured it out, and the issue is that there's a bug in the way that the UI here works, and so I had to unfortunately drop down to writing the SQL for it. What I did was I did an alter table, courses, add course ID int identity not null, and I ran that command. And when I ran that command, what it did was it added this, and that's what I was trying to get it to do before, and I couldn't get it to do through the UI here. See, I kept checking this button and it kept never saving the option that I was checking. So problem solved. So what you want to know is now every one of these courses has a unique number. Now, this is still set as the primary key. Let's change that so that course ID is the primary key. Okay, so let's change this from course code to course ID. Oh, I probably got to drop this one first, and then I got to add it back in. All right, course ID. Okay, now it's done. So now the primary key of this table is course ID. So let me demonstrate this. Let me add a row. Let's add in, let's add in history 401. Oh, history 401. And let's say European history. And let's save. And I'm not putting in a course ID, right? So I save it. It automatically adds a course ID. That's a surrogate key. It writes the value for you. Now, here's the problem with surrogate primary keys. This is, not really part of the tuple. This is some made-up implementation thing, right? So now I technically don't have entity integrity anymore. This table is no longer a relation because I can do this. I can make this mistake. I got the same course code in there. I could actually have the same course title in there too, because there's no constraint there. And it just goes along its happy way, giving it a new number. So we're going to see how to fix this in a little bit. But, first things first. So again, surrogate keys, it generates the value. You don't have to worry about what the values are. They just get made up for you. All right, let's talk about the columns in the table now. We've spent enough time talking about the rows. Let's get into the columns. You have two aspects to a data domain. You have the physical domain, that is how the data in the column are physically stored, and then you have logical domain, which is what makes sense to go in this column. So these two are not 100% compatible with each other. It can be very difficult to implement logical domain, even though that's what you ideally want. The physical domain can only get you so far. So let's take a look at physical domain first. This is a requirement. Physical domain is a requirement of every column in the table in a DBMS. It needs to have a physical domain, as you saw when I was using add minor. So you have different types of physical domains. You have integers, decimals, floats, characters. Okay, characters are fixed length characters, like I say char2, and that means characters of size 2. Varchar means up to 2 characters, so it's a little more flexible. Why would you have both here? Well, if you have char 100, it's always going to store 100 characters. If you have varchar 100, it's going to store 2 characters plus, a little extra data that says there's 2 characters in here. And then if you have 100 characters, it'll store 100 characters, right? So it has to store a little bit of metadata with the actual data that says how big it is, right? So it's a little slower, but you save on the storage. So there's always a trade-off between processing and storage when it comes to data. You also have a date type, a time type, and a date time type. Makes sense. You got just for dates, just for times, and for dates and times. These are physical domain, right? So, for instance, if you're going to store a student's an employee's date of hire, you might store that as a date, right? You don't want to store that as varchar, because then you can't compare one date to another date, or you can't easily figure out if that person was hired in January, for instance. So there are things you can do to dates that you can't do to characters, right? Likewise, if you're going to store a student's GPA, you don't want to store that as a character. You want to store that as a decimal so that you can do math on the GPA. Okay, so let's talk about how we implement logical domain. This is done through data integrity constraints. Okay, there is a unique constraint which functions like a primary key but does not affect the physical ordering of the data in the table. The unique constraint is what we use to reestablish entity integrity over our natural key when we have chosen a surrogate key, right? So going back to that class, the course example, right? We had that the course ID, which is 1, 2, 3, 4, 5. That's a surrogate key. That's the primary key. That optimizes data insertion. But now we have lost entity integrity because our natural key, course code, is no longer used as a primary key. So the way we reestablish entity integrity is by using a unique constraint. That's basically it in a nutshell. There's also a check constraint. A check constraint is a Boolean expression which must be true prior to the data being written. So this is a way to enforce, don't put bad data into my table. Don't put a date or a numerical value that's out of range. There's also a default value constraint, and a default value constraint is used to put a value in when one is not specified. All right, it's demo time again, and we're going to look at the data domain one more time. And we're going to go back to add minor, and we're going to do all of the following here. We're going to add some more columns and then add some constraints to show you how constraints can be used to control the data that goes into the table and to keep the data as accurate and as meaningful as possible. This is actually one of the really nice things about a relational database is you can really get close to enforcing true data domain with these data integrity constraints. Okay, we're back in add minor. Let's go over there and alter that table again. And we have course title and we have course ID. Let's add course credits. Course credits, and let's make this an integer. Let's go with tiny int because you're not going to have 100 credits, right? It's either 0 or 6. And let's add a default value. If you do not specify a course credit, it will use 3 as the course credit. And then let's add a course college, and let's make that a varchar. I guess 10 is fine. And let's put a default college in there of business. Now let's see what the heck that did. So let's go to the table. And you'll see now everybody has 3 credits, right? That's the default value, right? So there were these values that were already in here. They got the default value. Now I can override these values as I see fit, right? I can put in this IST one should be maybe it's 1 credit, and this is information college. There. Whoop! I spelled it wrong. Dadgummit. There. Okay. Oh, it's just cutting it off. Oh, you know why? There's more than 10 letters in there. Oh boy. See, well, that gives you a great that's a problem with varchar 10, right? I had 11. Information's 11, so let's make it 15. Alter table. 15. Save. And let's go back. Edit. Information. Save. And then now we have an N. All right. Okay. That's good. So let's put in a check constraint. Now, I was researching this as well, and I don't know if there's a way to use adminer to put in a check constraint. So I'm going to, once again, fall back to an SQL command. I'm going to alter table courses, and I'm going to add a constraint, and I'm going to call it CK valid credits. And I'm going to make it a check constraint. And what I want is the course credits between, maybe I should move down a line. 0, 1, and 6. So the courses have to be either 1, 2, 3, 4, 5, or 6. They can't be 8 credits or 0 credits. So I'm going to execute that. All right, I probably goofed something up when the spelling. Let me try that. Okay, yeah, I forgot my parentheses around the check constraint. Okay, so I have added my check constraint because all of my data already satisfies. Let me go back here. Oop, okay, because all my data already satisfies that data integrity constraint, I didn't get an error that says you have invalid. You have invalid. I cannot set the constraint if this isn't satisfied, right? So let's break this now. Let's take this accounting too. Let's say it's like a 9 credit course, and watch what happens. Okay, it says you can't do that, dude. It says you violated a check constraint, and that's the name of the check constraint. And the conflict occurred in this database tinyU. So that gives you a great example of how to enforce data domain when you just have physical domain. When you have to go beyond physical domain, you can use the check constraint and the unique constraint to do that. Now let's play around with the unique constraint, right? I got this accounting 120, right? If I were to add a unique index here to course code, it's not going to let me do this because I already have ACC 120 in there twice. See that? Duplicate value is ACC 120. I got to fix that first. So let's fix that. Let's say this is going to be ACC 121. Save. And now I can add that constraint. Let's add a unique constraint over course code. Done. Now let's go back to the data and let's try to mess around with it. I'm going to change this IST 102 to 101 and watch what happens. It's going to violate that constraint again. Cannot insert duplicate row. So this is why it's important to name your constraints, as we'll see later on, as you want to make this easy for whoever's using your database to understand what kind of rule they violated, right? It's not very easy when it just says courses course code. You should probably call this unique constraint course code on courses or something like that, so that they understand what rule was violated. Okay, anyway, that's a unique constraint, and that's how we enforce entity integrity when we make the decision to use to use a surrogate key as the primary key, as we did in this case here. So that way we can put a unique constraint over this and then still get the entity integrity we need. Okay, it's time to address nulls and flags. So let's talk about the elephant in the room, that is null. Null is the absence of a value. It is not a value itself. It just means that no value was entered. And this is okay in some circumstances, but in other circumstances it can be problematic, mainly in text columns. Generally, nulls with dates make sense. It either has a date or it does not have a date, right? Sometimes nulls in numerical values make sense. Like, for example, when you're a brand new student and you're starting college for the first time, what should your GPA be? It shouldn't be 0. It shouldn't be a 4.0. You don't have a GPA. It should be null, right? And then after your first semester, then you have a GPA, right? So null makes sense in certain circumstances. Where it becomes a problem is when null takes on multiple meanings. For example, null's okay here because this gentleman here, Curtins, he left the company on February 14th, 2020. And therefore, he does not have a benefit plan because he doesn't work there anymore. Now, this other gentleman down here, Dustin DeWind, he still works for the company. So why is his benefits plan null? Don't know. No reason. So generally, the way we handle this is with a flag. What we do is we don't allow null in the benefits plan column, and instead we have special values to imply the meaning as to why the values are null. So these are the old values in here. And then I have a value called not applicable terminated and another value not applicable opt out. And those represent the flags that designate that as to why that value would have been blank, but now it's no longer blank. All right, now we're going to get into how do I take one table and another table and establish some kind of link or bond between them so that I can associate these isolated sets of data with each other, right? And that is called referential integrity, and referential integrity gets implemented via foreign keys. So referential integrity is a characteristic of a column in a table which ensures that the values in that column are null or are represented as a primary key in another table. I know that's a mouthful, but of course I'm going to beat you up with a bunch of examples. We achieve referential integrity in the DBMS using a foreign key constraint, the constraint on a column in one table which references the primary key column in another. There can be several foreign key constraints within a table, but there can only be one primary key constraint within a table, right? But in that same table, you can have 9 or 20 foreign key constraints. The same primary key can be referenced by several foreign keys. And I can give you a conceptual, proof of that. So a student might appear in many clubs, right? So in the clubs table, you might have a column that says this is the student ID of the student in that club. Likewise, a student can be enrolled in many courses, right? So you can have a student ID and then be a foreign key into some kind of enrollment table that tells you which student is enrolled in which course. So these foreign keys can appear all over the place, meaning that copies of the primary key values can appear in all sorts of places. So let's do an example. So here's my table of employees, and I have highlighted an employee named Hugh Japple here. And the primary key of the column is the one that's underlined by convention here. So the ID column is set as the primary key constraint of the employee table. This gives us entity integrity. I would probably have a unique constraint over the natural key SSN as well, now that you've learned this, to guarantee that I cannot insert two Aurora Borealis people into my employees table. So employees get paid. Every time you get paid, you get issued a paycheck. So I have another table, paychecks. And the paychecks table has a row for every physical paycheck that gets printed. But as you know, I don't print paychecks in the ether. These paychecks belong to employees. So the way I track whose paycheck belongs to which employee is to not embed the employee information in the paycheck, because that would be not repeating myself. I'm violating the dry principle. So instead, I create a foreign key column. In this case, it's employee ID. And the employee ID column is representative of the ID column in employees. So I can't have an employee over here that isn't an employee over here, because that would make no sense, right? All of a sudden, hey, you got a paycheck and you're not an employee? What? Okay, that would be bad. And then this is how I can refer to whose paycheck it is. So you see, I've taken all of Hugh Japple's paychecks and I've highlighted them. So 33, 33, 33. That is those three paychecks belong to Hugh Japple. So basically, that is how a foreign key works. Is it establishes a bond between two tables so that you can associate the rows in the tuples or rows in one table with the tuples and rows in another table. So later on, we're going to learn how you can combine these two tables together when you ask for the data back out to get a single result. And this would be how a business application would print a name on a paycheck. At the database level, they don't store it all in one table. That would be that would be violating the dry rule. You're repeating yourself, right? Because then you'd have Hugh Japple here, Hugh Japple here, and Hugh Japple here. And when Hugh Japple decides to change his name, now you got to change it 3 times. Okay, that's not good, right? So the better way to approach it is with a foreign key value. So this is what makes relational databases what they are, is entity integrity and referential integrity. So let's talk about a very special type of foreign key called a lookup table. So there are times when we want to establish a data domain over a varchar column. Like, for instance, we might have a table of students, and we want the student year to only be freshman, sophomore, junior, or senior. We don't want any other values in here. We don't want people to put in super senior or pre-freshman or anything like that, right? We want to restrict the values to those 4. So the way we do that is we establish this as a foreign key, and then we make a table, excuse me, that only has the unique values that we would like them to be able to choose as primary key. And you can even give it an order. So like, freshman's first, sophomore second, junior third, senior fourth. And this table is pretty static. It never changes. But the reason that it exists is to help us with selecting a choice. So you've seen this probably in user interfaces when you see a drop down of values. The values provided in the drop down come from the lookup table, and what gets written as you're filling out the form or whatever, it goes in as an entity in the students table. So, which student is this? I pick this Johnny as a freshman, and I just pick freshman and I'm good to go. So lookup table, very special instance of foreign key. And basically, there isn't a primary key table. You make one from the set of acceptable values over the student year column. right, it's time for another demo. This will be our last demo. We're going to go back to add minor, and we're going to add some foreign keys. We'll add a lookup table that only allows you to enter colleges that are in the lookup table. And then we'll demonstrate that through, demonstrate how referential integrity works through the foreign key constraint. Okay. All right, we're back in add minor, and what we're talking about here with this demo is this course college. I do not want someone to be able to type in whatever they want. I don't want that to happen. Now, granted, the way the admin user interface works is I can type in whatever I want. But what I want to do is I want to restrict the data domain of course college to only be the values that I specify in a lookup table. And that's number one. And then number two, what will happen is if I do try to type in something like this, it just won't save the data, right? So that's what I'm looking for out of a foreign key constraint. So let's establish the primary key table first. So I'm going to call this colleges. And I'm going to put in a column name called college name. And it's just going to be a varchar 15 again. And that's going to be good enough. I could have like college address and website and all that stuff, but we're just going to keep it very simple. Then I need to set a primary key here on that college. Do that. Okay, then let's go put some data in. And let's put in the School of Information. And I'm doing this on purpose, right? So I put information first. Then I'm going to add accounting. And notice that accounting comes before information, even though I added information first. This is what I was saying before about when you select a primary key, it affects the physical ordering of the data in the table. So let's add, I don't want an accounting school, I want a business school, right? Okay, let's add another school here that goes between business and information. Let's add the engineering school. Watch what happens. It goes boop right between the two, right? Again, that is because the primary key is college name, and that affects the physical ordering. This is okay for smaller tables, but when your tables start to get up into the 6 figures, 7 figures of rows, it's going to be very problematic to performance, especially if there is a lot of inserts. Okay. So I've got this. Now let's establish the foreign key. So I don't know if I can do this in add minor or not. I may have to write SQL to do this. We're going to find out. Let's go back to colleges. And oh, there's an add foreign key. Great. Okay, so I'm going to add a foreign key here. And the source, this is the primary key. It's going to be college name. And the target is going to be college name. So basically, this, oh, did I do that right? I think I did that wrong. Drop that. That's wrong. I made a foreign key to itself. I got to pick the right table, Mike. I need to pick courses and then add foreign key. And then the source table, the target table is colleges. And the source is course college, and the target is college name, right? So college name comes from the colleges table, and course college comes from the courses table. So this is the foreign key table. That's the foreign key column. The primary key is in the college table, college name. So if I pick this, like if I pick majors, right? See, I don't have that in there. It's a different one. So I'm going to pick colleges again. Now I've got a foreign key. So what does this actually buy us? So let's go back to our data again. And I can take this accounting one here, and I can, I can't do busyness anymore. this won't fly because it's going to violate that foreign key constraint. Okay, foreign key constraint there. So that is another way that you can enforce some data domain over the data in your table. I can take any of these though. There's nothing preventing me from just being foolish and doing that, right? And just assigning that to engineering. There's no, I can't prevent people from making mistakes. Like, the history course is in the engineering department. There's no way around that, but at least you are restricting the values that they can put in here. Okay. So that's basically what a foreign key does. What's kind of interesting about AddMiner is these now become links, and they obviously take you to that row in that table, which is kind of interesting. All right, we covered a lot, so let's sum up. A DBMS table consists of rows and columns. It's best practice to have entity integrity on your tables. We do this by using a primary key constraint. The best primary key is usually a surrogate key, and when you do that, you'll want to make sure that you have a unique constraint over your natural key. Physical domain is implemented with data types, and every single column needs an established physical domain. Logical domain is implemented through data integrity constraints. That is a check constraint, a default constraint, a unique constraint, or by using a foreign key constraint. And the use of foreign key constraints establishes referential integrity, right? So that it guarantees that the values in another table come from the set of values in an affiliated primary key column in a different table. Okay, that's it. We'll see you next time.